Hello, students. Welcome to Fatigue Analysis for Extreme Environments. I'm Dr. Stewart. Today, we're going to be covering a chapter on notches and their effects. This chapter is going to be split into several videos where we focus in on different aspects of notches. Today, we're going to focus on stress and strain concentrations. In future videos, we're going to look at how notches are dealt with in the stress life approach, the strain life approach, linear elastic fracture mechanics, the two-stage approach, and then we'll make some general discussions about do's and don'ts when dealing with notches. Let's get started. Stress and strain concentrations. Stress and strain concentrations tend to persist in most of the structures and machines that we design today. It's simply that notches, grooves, channels, welds, keyways on shafts, that these different types of structures are required in order to make a mechanical design function. Although notches and grooves and things to that effect can be dangerous, we can render them harmless by suitable treatment, by thinking carefully about them and designing our structures appropriately. To understand the effect of notches, one must consider 5 different parameters. The first is the concept of stress and strain concentrations. Second, the concept of stress gradients in the vicinity of those concentrations. Third, the effect of mean stress and residual stresses, again, near notches. Fourth, what happens when we plastically deform, when we yield in the vicinity of a notch? And last, what happens when a crack grows at the notch? So in this chapter and in the slides, we're going to go through and see how each of these concepts apply. Let's start with a stress gradient. A stress gradient is defined as a geometric discontinuity causing a local amplification of the stress and strain fields. We tend to define a stress concentration factor. We call it a capital KT or KTS, which is a ratio between the local maximal stress, so sigma, the local stress at the notch, and the net stress, which is the nominal stress in the structure, which is a stress that's measured in the ligament by the notch. In our next slide, we'll get a better understanding for what that means, but in essence, it is the net section that we are going to be measuring. Now, let's get a little bit more of an idea of that concept by starting with the nomenclature. The KT is the axial or bending stress concentration factor. KTS is the shear stress concentration factor. The sigma and eta symbols, those are the local maximal stresses. Those are the values at our notch. The maximal values right at our notch, right? At our discontinuity. Now the S and the E, those are the net stress or strains. And these are measured in the local ligament area. So this area that is in the vicinity of the notch, but they are measured as an average value with respect to the remote loading. So with P, this remote force over that ligament area. Now, a wonderful thing that we have is there's a bunch of great mathematicians who've applied the theory of elasticity to different types of structures and loading conditions to give us the analytical solution to the stress field and strain fields near notches and grooves, right? An example of that is given here for a circular hole in the center of a finite width sheet that's in tension. So applying the theory of elasticity and doing a little bit of calculus, equations that describe the stress field have been derived, describing them as a function of the radius of the hole, as well as a function of the distance, so an actual position from the tip of that hole, right? From the radius of the hole moving outwards. So this actually gives us a X and Y positional information about how the stress field changes near the notch. Now, for deep and narrow notches with semicircular ends, a formula analogous to linear elastic fracture mechanics has been given. This is a way for us to almost extend this stress concentration or stress field equations to something that might be a very fine crack. And that gives us this following equation, that the stress near this sharp crack is equal to a maximum times the square root of a term of the radius of the hole as well as the depth of the sharpness of that crack. Now, stress concentration factors, these charts and as well as the stress field equations, can be obtained not just from the theory of elasticity, but they also, and most commonly, are obtained from numerical solutions, such as the finite element method, where the geometry and loading condition is simulated in a finite element software, assuming a linear elastic material, and with fine enough mesh, you're able to approximate what the stress field is and what the stress concentration factor is for that geometry. A third method does exist, and that is to experimentally measure the stress field or strain field within a representative sample. And ways to do that do exist. In fact, experimental measures and methods, that was the way to validate the theories that were derived back in the day from the theory of elasticity. So ways that people have done it include applying a brittle coating to a material and looking at, as that coating cracks, seeing the strain fields through the cracking, the pattern, the crack patterns in the coating. There's photoelasticity, which is probably one of the more popular methods. There's the thermoelasticity method, and then there's also the application of many strain gauges to figure out what the strain field is. Now, the numerical method, again, would be to create a representative geometry with a fine enough mesh so that when we simulate under linear elastic conditions, we can get a good approximation of the stress field. So the stress is in the y direction, the x direction, the shear, and then as well as an equivalent von Mises stress. Focusing in on the experimental method, photoelasticity is a method where we create a sample with a specific geometry and loading condition of interest out of a birefringent material. And then we place that sample within a polariscope, and then by changing the optical orientation, the angles of in the polariscope, we're able to identify isocline patterns within a sample. Now, some of you may remember in class, this is a sample that I designed way back in the day when I was a student. So I actually did this experiment here. So what is the process? First, we will capture fringe patterns at different isoclinic angles relative to our loading direction. So as we rotate the mirror within our polariscope and get to these different angles, we can capture these images. Once we've captured the images, then what we'll do is we'll trace the isoclines from so we process these images, we create a 0 or 1 pattern and then create isoclines around that. And then we compose those isoclines at each orientation to generate stress field patterns. So this is here us tracing the isoclines, and then lastly composing those isoclines together to generate patterns. And this image here is comparing what came from a finite element simulation and then what came from the actual photoelasticity experiments. And then this is another example of a disk that's diametrically loaded. So these are images taken at different angles, and then this is those patterns composed and compared to numerical simulations. So overall, this shows that we can use the theory of elasticity. We can also apply numerical methods, or we can experimentally determine these stress field and strain field equations and subsequently figure out what the stress concentration factors are. Really, the best approach right now, the modern approach, is to design a well-posed finite element model, and then we can figure out for complex loading conditions what our stress concentration factors will be. Because in truth, real components are subject to complex loading. That makes it difficult for us to experimentally verify or to even apply the theory of elasticity to derive the equations from. So overall, though, for most and for many different geometries and loading conditions, for many of the ones that we do see commonly in structures, equations have been derived, whether empirically from experiments or from the theory of elasticity. And really the most important source that we can get for these equations, for these charts, is Peterson's stress concentration factor book. This tome, this 1,000-page book, includes almost every condition you can conceive of. And of course, if there's a condition that we can't conceive of, let's apply the finite element method. Now, when we do go into the book, or we do apply finite element method and do our parametric analyses, we end up with stress concentration factor charts. This here is an example of stress concentration factor charts for a stepped shaft that is subject in A to tension, so we have a tensile load, in B to a bending moment, and then in figure C here to a torsional loading. In reading these charts, we need to focus on a few things. First, let's look at the x-axis, which is a dimensional ratio here between the fillet that steps the shaft down and the smaller diameter of the shaft. Within the plot, there exists multiple lines. Each of these lines is also a dimensional ratio, a ratio between the larger diameter of the shaft and the smaller diameter of the shaft. And then lastly, the y-axis here, that is our stress concentration factor. How much the stress in the vicinity of the notch is increased in comparison to that net stress, right? That KT value is on this y-axis here. So how do we read this chart? Well, first we decide what our dimensions will be. We plot up to the proper line, we plot over, and then we get an idea for that KT value. Now these charts are, again, specific to the loading condition, but also to the type of geometry. Here we have an example of stress concentration factor charts for a flat bar with opposite U-shaped notches on opposite sides of it. In A, we have it loaded in tension, and in B, we have it loaded in a bending, right? And we can see that this chart, again, is a little bit different. But if we look at it, some things remain the same. Our x-axis is a dimensional ratio. In this case, the radius of that U-shaped hole to the distance between the two U-shaped holes. We have multiple lines, which again, each of them is a dimensional ratio, a ratio of h, the total width of this bar, to d, which is the distance in between the U-shaped holes. And then our y-axis is our stress concentration factor, right? So these charts have been prepared for many, many geometry. And we have books available for them so we can look them up. The charts can be presented as equations, which could be easier for us to use. And numerical methods, finite element analysis is a good way if we have a unique geometry to approximate what those stress concentration factors are. Now, there is another approach that we can use to qualitatively kind of assess the effect of a stress concentration. It works mostly for very simple loading, but it can help us to figure out or help us to do design thinking and figure out how to maybe mitigate stress concentrations. The method is where we compare stresses and strains, the fields and the development of them, to fluid flow, to a liquid flow, where when we see the flow lines concentrate or become more closely packed, we consider those locations to be places of higher stress concentration. Okay. So what do we want to do here? Let's get the pen. So how do we define that? What is this liquid flow concept? Say we have a sample, such as this, that we are loading in tension or loading it in compression. Let's replace that loading concept with fluid flow that has the same unit direction vector as that force that's being applied to the structure. As we say that this is a uniform flow, we would expect, or we could conceptualize very easily, that as this fluid flows down the pipe, which becomes what this specimen is, that it must concentrate as it moves through a reduced cross-sectional area to this reduced next section, right? And that there might even be, in some case, some stagnation zone over here, this little corner, where the material or the fluid does not move at all, right? Things do not flow in, things do not flow out. So this concept, this fluid flow concept, is exactly what we're looking for. The lines of the fluid, or the fluid pressure, is expected to increase around the bend of that notch, right? And we would also expect, since there's this stagnant zone here in this corner, that this would be a location where stresses are extremely low, because there is no reason for the force to really flow in that region, right? So if we look at this particular specimen, we can see, hey, there seems to be a fairly sharp concentration at these two U-shaped notches, right? We can do the same thing with different geometries. Say we have this geometry, which has a much shallower radius, and we replace the remote loading with some fluid flow that is uniform and has the same unit direction, or opposite direction. It has the same unit direction as the force load, just for simplicity. We can see that since the stress concentration, or since the change in geometry is much shallower in this structure, the concentration of our fluid flow lines is lower. So we would expect, in this case, if we're comparing the two geometries, a lower stress concentration in this structure. So just based off of this concept of fluid flow, we very quickly can determine between two different designs which one will produce more stress concentration. Taking this concept further, we can look at a bunch of different geometries and quickly figure out ways to mitigate, to reduce stress concentrations, and even to remove material where there are dead zones where stress does not flow at all. So some examples, say we have this is a chart that shows examples for poor fatigue strength versus ways to reduce that stress concentration and improve fatigue strength. Our first example here is a plate that has a center hole. It has poor fatigue strength as is, but we can mitigate it by adding stress relief holes to modify the stress field, or to just have those holes directly modify that circular hole. Here's an example for a bolt connection. And we can see that overall this design has some very sharp edges in different places. It has poor fatigue strength. How could we improve it? Well, in this case, we put some stress relief holes that get rid of that sharp edge and give us kind of a more rounded edge for our stress to flow around, right? These same concepts apply to different shafts, holes, grooves. These are very standardized stress relief methods that work with this qualitative measure or qualitative method. So that is the end of our stress concentration factor video. Join me next time as we look at the stress life approach for notches.